Hi, I'm Marius from Mental Model Space, and this is part 2 of Introduction to Systems Theory. In this video, we'll be discussing the basics of system structure. I'll start out by defining what a system is, and then we'll build some systems, starting with some simple examples, moving on to bathtubs, and finally concluding with feedback loops. One way to define a system is as a set of interconnected elements with a specific function or purpose. We'll see that this is a fairly broad definition, but it's nonetheless useful. The key terms here are the elements, their connections with each other, and the specific function or purpose. And I'll be going through each of these terms in the following slides and elaborating and giving examples so we can better understand what they mean. The elements of a system are just what they sound like. They're the things or the stuff that make up that system. So to give an example from nature, we could think of plant cells as being the elements of a leaf. We could also think of that leaf in turn being an element in a tree, or that tree being an element in a forest, and the forest could in turn also be an element in a larger ecosystem. So what we see from these examples is that elements are relatively easy to spot because they're sort of the things that make up the system. And their choice in some ways also determines the granularity of the model we're using. So for example, it wouldn't make sense to model an entire forest with plant cells as being the elements because that would be way too complicated. So if we choose the plant cells as an element, we're probably only looking at the system of a leaf as a whole. Also, we see that elements may themselves be systems. So the leaf is at the same time an element of the larger system of the tree, but it also forms an entire system where the plant cells are elements. So we can have systems nested within systems. To give an example from society, we might think of a university as being a system. Here, individual students might be elements, we could have study groups being elements, we could have the sports team being an element, and also we can think of the buildings and the infrastructure as being elements of the university. Here it's worth pointing out that even though in all the examples I've given, the elements have been physical objects, they can also be intangible. So we can, for example, think of the university's reputation as being an element, or also an individual student's skill level as being an element in the system. Despite the fact that elements are sort of the most visible part of systems, changing them usually only has a minor effect. So consider, for example, swapping out individual trees in a forest. That's probably not going to impact the ecosystem a lot. Or if we're thinking about a university, there's a constant influx and outflux of individual students, yet somehow the university still manages to retain its integrity as an institution. The connections in the system are also pretty much what they sound like. They're the things that allow the different elements to interact with each other. So in the example of a tree, we might think of the vessels that allow for transport of water and nutrients as being the connections between the different parts of the tree. In economies, we also need to transport physical goods, and here we can think of the train lines and the roads and the shipping routes as being the connections of the different parts of an economy. Often, though, we're not interested in transporting physical goods, but instead we're interested in information exchange. So here, if we think of a company, for example, we could have direct information exchange by a speech between two people, but we could also have memos and phone calls and such. And obviously, the internet connects pretty much all electronic devices at this point, which also allows for mass communication. Compared to the elements of a system, the connections are usually less obvious, since they're usually non-physical and often involve information flows. Despite this fact, changing the connections of a system has a large effect on its behavior. Think, for example, of the effect of changing trade agreements between countries would have on their economies, or how disrupting communication between two departments in a company could cause that company to collapse. The function or purpose of a system is generally its most abstract part. I'll be trying to use function for non-sentient systems and purpose for human systems, but I might get them mixed up from time to time. If we think back to the university, its primary purpose might be to educate students, although it also may have a secondary purpose of earning money. So in general, systems can have multiple purposes. If we think back to the tree, its function might be to convert CO2 into oxygen. And in general, one really important function of nearly all systems is self-preservation, or the preservation of their own integrity. So systems that don't have this function generally don't last very long. And in nature, this can take the form of trying to survive, Or in society, this could take the form of securing existing power structures or trying to keep your wealth, etc. Because functions and purposes are so abstract, they're often the least obvious part of a system. Added to this, there's the complication that often the stated purposes of a system aren't its actual purposes. So we might imagine a spokesperson for the university saying that it's their top priority to educate students, but in fact the university is acting as though it were their top priority to maximize their income. So in these cases, we need to pay attention to what the actual behavior is and not just what some spokesperson says. As you might imagine, changing the purpose of a system will radically transform the way that system behaves. So if the school from before, for example, shifts its focus from primarily trying to educate students to primarily trying to earn money, that will fundamentally transform the way that that institution operates. Or if we think of a sports team, if they change their purpose from trying to win games to trying to lose games, that will obviously have a huge impact on the way that sport works. So this is the first sort of counterintuitive but really important insight that systems theory provides. It's that the least obvious part of a system actually has the largest effect on the system's behavior. Putting it all together, we can give some examples of systems now. So we can think of the rabbit as being a system with its organs being elements connected by blood vessels, and its function is to survive and reproduce. We can think of the tree again with the leaves, branches, trunk being elements that are connected, and its function is also to survive and reproduce. We can think of the sports team as being a system with the players being elements that are connected via communication and the ball, and their goal is to win the game. And we can think of the university again with its diverse set of elements that are all connected in order to ideally educate students. So we see that many things are systems, and the question might occur, what is not? So a random assortment of objects, for example, wouldn't be a system. So if we think of a rock pile, it doesn't really have any connections between the rocks, and there's no really overarching function or purpose. Also, if organisms die and lose their integrity, they also cease to be systems. They're still part of sort of the larger ecosystem, but they themselves have lost their systemness. Now that we hopefully have an increased understanding of what systems are, we can start to build models and see how these models behave over time. We'll be modeling the elements of a system with stocks. Stocks are basically what they sound like. They're stores, quantities, or accumulations of stuff or information. And we'll be modeling the connections by flows and feedback. So flows transport stuff to and from stocks, while feedback changes the rate of these flows based on stock levels. The simplest model we can build using the components I just mentioned is basically just an isolated stock. In my diagrams, I'll be using these dashed gray lines to indicate the model boundary, and everything outside of that boundary we kind of ignore for our modeling approach. So it's hard to find actual real-world examples for isolated stocks, but one example might be a mineral deposit on the moon, where no minerals are going in and no minerals are coming out. So consequently, over time, the level of that stock will just remain constant. We'll often be using these behavior over time graphs, where on the horizontal axis we have time plotted, and on the vertical axis we'll have the level of some stock plotted. It's often not important to look at the exact numbers in these plots. What's more relevant is the shape of the curves and what that means for the behavior of the system over time. Considering the mineral deposit on the moon, there may in reality actually be in and outflows into it. There may, for example, be processes by which minerals are slowly created and processes by which they're slowly degraded. There may also be asteroid impacts into the moon which take out chunks of material, etc. So the take-home message here is that models always simplify. And also it's important to think about the timescales we're using for our models. So the isolated stock model may be appropriate if we're thinking along human timescales, so hundreds of years, right? But it may totally break down if we are moving to think about like millions of years of time passing. Next up, in terms of complexity, is a single stock with a single inflow. So places where this model could be appropriate is, for example, in the case of a landfill or an atomic waste deposit. Basically anywhere where we're putting things into a place but not taking anything out. So the way this system behaves over time is pretty straightforward. Basically, the level of the stock will just increase depending on the inflow rate. So you can imagine if we have a very large inflow rate, then the level of the stock will increase very fast. This results in a correspondingly steeper curve. And if the inflow rate is low, then the level won't increase as quickly and the curve will be more shallow. In the real world, it's always important to think about maximum capacities. So, well, in our model, we may not have sort of a limit to how high the level of a single stock can go. In the real world, landfills will fill up. There will only be so much place to put our atomic waste, etc. So these considerations are important when we're applying these models in practice. The next model we'll consider, which is a single stock with a single outflow, basically is the opposite of the thing we saw before. We can use this model to represent things like mineral or oil deposits that are being exploited. The behavior over time of the system is also pretty straightforward. Basically, the level of the stock will just continue to decrease based on the outflow rate. So if that outflow rate is high, the stock will decrease more rapidly, and if it's low, the curve will be more shallow and the stock will decrease less rapidly. In the real world, we have to consider that no stock is unlimited. So once the level of our mineral deposit hits zero, our mining operation will be over. So the three previous models we looked at were all pretty trivial in terms of behavior. And so what follows is going to be the first one that really shows interesting behavior, which is that of a bathtub. We can model a bathtub by thinking of the tub as being a stock of water with an inflow from the tap and an outflow from the drain. So throughout our lives, we've all probably become pretty familiar with how bathtubs work. So basically, there's kind of four things we can do. We can fill the tub by plugging the drain and turning on the tap. When we want to stop filling the tub, we just turn off the tap with the drain plugged. When we want to rewarm the water in the tub, we can turn on the tap to hot and unplug the tub at the same time. So there's like a flow of warm water through the tub. And then finally, if we want to empty the bathtub, we can just turn off the tap and unplug the drain. If we plot these individual steps in a behavior over time graph, we get something that looks like this, where in the first step, when we fill the tub, we have this linear increase in the water level up to the desired level. Then when we stop filling it, obviously the water level will remain constant. And then when we're rewarming, provided that the inflow through the tap is the same as the outflow through the drain, the water level will again remain constant, even though we have this flow of hot water through the system. And then finally, when we're emptying the tub, we have a linear decrease in the water level until the tub is empty. So one thing that becomes apparent here is that the level of a stock is influenced both by the current flows that are going in and out of the stock, and also by the flows that were happening previously, for example, when we filled the tub. So in some sense, stocks are the system's memory of changing flows. Despite being a relatively simple system, the bathtub can teach us valuable lessons that hold in general. First off, it teaches us that if the sum of inflows into a stock are greater than the sum of outflows, that stock will rise. This was, for example, the case when we were filling the tub. Conversely, if the sum of inflows is smaller than the sum of outflows, then the stock will fall. So we saw that when we were emptying the tub. And if the inflows are the same as the outflows, then the level of the stock will remain constant. Another lesson we can learn from the tub is that just because there isn't a change in the level of a stock doesn't necessarily mean there isn't a flow through that stock. We saw this in the case of the rewarming of the tub, where we had the tap set to the same amount that was draining from the tub. So here the water level remains constant, but we still have this flow of warm water that goes through the tub. Furthermore, stocks allow in and outflows to be temporarily out of balance. So consider, for example, the reason why we have bank accounts. It would be really tedious if we would have to spend our income at the rate we got it. So basically, on the one day of the month where we get our paycheck, we'd have to spend all of it and buy all the stuff we need for the rest of the month. So in the case of a bank, right, our account is a stock which allows us to store that money so that we can decouple our incomes from our spending habits. Finally, when considering this bathtub, we see that changing the flow rate is much faster than changing the level of a stock. So it's much quicker to turn off or on the tap or unplug the tub than it is to wait for it to fill or for it to empty. This means that in the context of systems, stocks act as buffers. And it's generally true that if it took a long time to fill, it'll probably also take a long time to empty. So this is relevant, for example, if we're thinking about weight loss, where if you put on weight over the course of years, you probably won't be able to lose it overnight. Same goes for things like pollution. Like if you spent decades polluting a lake or the air, it probably won't take just months to fix that problem. So far, in the systems we've examined, the in and outflows from stocks have been independent of the levels of those stocks. But in general, this isn't the case. Usually, we tend to make decisions based on the levels of stocks. So, for example, we might adjust our spending habits based on the amount of money we have in our bank accounts. And sort of this process creates feedback. And feedback loops are a closed chain of causal connections from a stock through a set of decision rules, then through a flow and back again. So basically, we're adjusting the flows to and from stocks based on some decision rule and the level of that stock. We'll encounter two types of feedback, namely balancing and reinforcing feedback, and we'll be examining these more closely in the following slides. One simple system that contains a balancing feedback loop is that of coffee cooling or warming. We can think of this system as a single stock, namely the coffee temperature, that has one outflow, which is heat exchange with the environment. We also have a couple variables. We have the variable of room temperature, and then we have a variable that gives us the difference between the coffee temperature and the room temperature. So basically what this balancing feedback loop, which I've indicated with a B, is doing is taking the difference between the coffee temperature and the room temperature and then correspondingly adjusting the outflow of heat exchange. So basically if we have very hot coffee, the difference between it and the room temperature will be correspondingly large, and there'll be a larger exchange of heat with the environment than if the coffee were cooler. The same goes for iced coffee. If the coffee is very cold, then we have a large difference between the coffee temperature and the room temperature. So correspondingly, the heat exchange will be larger than if the coffee was closer to room temperature. We can illustrate this behavior in a behavior over time graph. So we see that we have this nice sort of exponential decay type behavior. And if we focus on the hot coffee, which is 100 degrees Celsius to start out with, so the red curve, we see that it starts out losing a lot of temperature, but then eventually levels out around room temperature. If we compare that curve with the orange curve, which is coffee at 40 degrees Celsius, we see that the coffee that is hotter cools down much faster in the beginning, which is indicated by the increased slope. The same goes for iced coffee. So if we have iced coffee, instead of cooling down, it will warm up gradually to room temperature. And if we throw dry ice in our coffee and get coffee which is minus 78 degrees Celsius, that's the dark blue curve, it will warm up much quicker than if we just have regular iced coffee at 0 degrees Celsius. Based on this example, we see that balancing feedback loops do what they sound like they would do, which is try to bring a stock to a desired level. In this sense, they're goal-seeking. Also, it means that in systems, balancing feedback loops are sources of resistance to change. Furthermore, balancing feedback loops act like springs, so the further away they are from their goal, the more they pull. And this has two important consequences. First off, it means that if we do encounter resistance and there's a balancing feedback loop at play, we might not want to pull harder because that would just mean that the feedback pulls back harder. This has as an effect that the dry iced coffee, in our example before, the dark blue curve, warms much faster initially than the iced coffee. And this has as a total effect that it doesn't stay cold that much longer than the iced coffee, even though it was much colder to begin with. Reinforcing feedback loops might be more familiar to us than balancing feedback loops because they occur both in the case of bank accounts and in the case of population growth. When we think about a bank account, we might model it as follows. So we could have the account value being a stock, and one inflow into the account could be the interest payment. And so the amount of interest both depends on the interest rate that the bank provides, but also on the account value. And because it depends on the account value itself, that's where we get a feedback loop, which in this case is reinforcing. When we graph the behavior of this system over time, we get these familiar exponential growth curves. So at 0% interest, obviously the interest payments will also be 0, so we'll just have a constant account value. but at interest rates of 3%, 5%, and 10%, we see that the account value is steadily increasing. And this increase isn't merely linear growth, because the rate of growth is actually also increasing as time goes by, which gives us this accelerating exponential type curve. As this example shows, reinforcing feedback loops amplify behavior of a system and lead to exponential growth or collapse. In the real world, we have to consider that there are always limits to growth. So if you think, for example, of a bacterial culture, basically they'll go on growing exponentially until they hit some limit, which in the case of bacteria could be a lack of nutrients or a buildup of some toxins. And then the growth will level off and you'll get an equilibrium. And so basically, because exponential growth is so fast, the limits of growth will also be hit pretty fast. Additionally, a cool trick is to know that if you divide 70 by the growth rate in percent, that's roughly the doubling time. So in the case of our bank account, at 10% interest, the doubling time for our account is roughly 7 years. We've now seen an example of both a balancing feedback loop in action and a reinforcing feedback loop. And we saw that balancing feedback loops try to bring the level of a stock to a certain desired level and stabilize it there, whilst reinforcing feedback loops sort of amplify what's happening to a stock. Another way to put that, if you look at the graphs, you can imagine that balancing feedback loops sort of try to attract the lines to a certain value, while reinforcing feedback loops try to repel them away from a value. And so now the question becomes, if you put both a balancing feedback loop and a reinforcing feedback loop into the same system, sort of who's going to win the tug of war? And that's going to be an interesting question that we'll look at when we look at more complex systems in the future. When considering the importance of feedback in systems, it's interesting to ask yourself the question if you can think of a single decision you make without consulting the level of a particular stock. So a decision that doesn't in some way involve feedback. And I think you'll find that it's really hard to find an example of a case where there's no feedback involved. So this indicates that feedback sort of is everywhere and it's really important. And finally, feedback provides a mechanism for this nonlinear type of causation I mentioned in the previous video. So even though A causes B, B may in turn also again cause A through reinforcing feedback. With that, we're almost at the end of this video. I'd like to briefly recap what we covered today. So we saw that a system can be described as a set of interconnected elements with a specific function or purpose, and we explored what elements could be, how the connections between them could look like, and what the significance of the function or purpose is for a system. We then learned, using the example of a bathtub, how general systems behave over time. And we saw that if the sum of inflows is greater than the sum of outflows from a stock, that stock rises. If the sum of inflows is smaller than the sum of outflows, that stock will fall. And if the inflows equal the outflows, then the stock will rest. But this doesn't mean that there's no flow through the stock, because the stock may also be in dynamic equilibrium. Then we looked at feedback loops, and we saw that feedback loops influence the rate of flows into a stock based on the level of that stock. And we saw that there's two types of feedback loops that we'll be encountering, namely balancing and reinforcing feedback loops, and we learned about their characteristic behaviors. Thank you for your attention. You can find these slides as well as other written posts at my website at mentalmodel.space. If you've enjoyed this video, feel free to like and subscribe. And with that, I hope to see you next week for part 3 of Introduction to Systems Theory.